Today we're doing 7.1 only, which is about continuous random variables. So when we talked about random variables, um, I told you a lot of stuff, but for right now, when I say random variable, I want you to think that there's a bag of numbers. Every time you hear the word random variable, think there's some big bag of numbers, and what we're going to do is we're going to draw once from the bag. That's like every problem that we're going to do every time we have a random variable. There's a bag of numbers, and we're going to draw once from the bag. But the difference between chapter 7 and chapter 6 is chapter 6 was discrete random variables. Chapter 7 is continuous random variables. I did not tell you what the difference is between a discrete and a continuous random variable. I didn't tell you what a discrete random variable was in chapter 6, but now that we're in chapter 7, I will tell you the difference. Okay, so let's go ahead and get started. So we're doing a different type of random variable today, continuous versus discrete. Again, chapter 6, those were discrete random variables. And all the stuff we learned, like you make a table to find the probability distribution, and here's how you find the expected value and standard deviation and variance and all that stuff. Everything I told you in chapter 6 was about discrete, a certain type of random variable. Now we're going to look at a different type of random variable called a continuous random variable. We have to know what the difference is between the two, like what's a discrete, what's a continuous, and then how do you do the stuff we did last class, or the last two classes when you're dealing with a continuous random variable. Okay. So just to remind you about what a random variable is before we start. Again, random variable, just think of bag of numbers. Okay, let's see what it says here. So I want you to imagine a bag with numbers in it, and we're going to draw one number out of the bag. Okay, every time I say random variable, there's a bag of numbers somewhere. If you want to know more about the story, yeah, there might be some more about the story, but the minimum thing to think about when I say random variable is there's a bag with numbers in it, and we're going to draw one number out of the bag. The number we draw out of the bag is the value of x. Okay, so x is the number that you draw out of the bag. Again, if you want to know more of the story, if you want to know where the bag of numbers come from, yeah, there's more to the story. Basically, the idea is there's some experiment going on, like flipping a coin once or more than once, or drawing a card out of a deck, or playing roulette, or rolling a pair of dice, or whatever. There's some experiment whose outcomes we relabeled with numbers. So we relabeled the outcomes with numbers because that's what I told you a random variable is. It's a way of relabeling all the outcomes of an experiment with numbers. But the end product is the bag, and that's what we care about. That's the most important thing. We end up with the bag of numbers, and we're going to draw once out of the bag. And okay, if you know, we talked about probability distribution of a random variable last class. And if you have the probability distribution of a random variable, then it lets you know a lot of information about the bag of numbers. It lets you know what numbers can be drawn from the bag. Okay, so probability distribution lets you know what numbers can be drawn from the bag and what the probabilities are of drawing those numbers out of the bag. Remember, it was a two-column table. If I say find a probability distribution for this random variable, you make a two-column table. The left column are all the numbers that are in the bag, and the right column are the probabilities of drawing those numbers. So once you have the probability distribution, you know lots of stuff about the bag. You know what are all the different numbers in the bag and the chances of drawing those numbers. And once you know the chances of drawing those numbers, you know which numbers are there a lot of and which numbers are there not a lot of in the bag. Okay, so I'm going to go through all that one more time. So again, when I say random variable, think of bag of numbers, and we're going to draw one number out of the bag. X is going to stand for the number we get out of the bag. It's called a variable because the value of X varies depending on which number we get out of the bag. I haven't drawn, so I'm going to draw some numbers out of this bag. Right now, I haven't drawn a number. So if I say, what's the value of X right now? It has no value. X is sitting there waiting for you to draw a number. And whatever number you draw, that becomes the value of X. So right now, value of X is nothing. There's no value. Now, if I go ahead and draw a number, now the value of X is 3. I've drawn the number 3. X becomes 3. If someone says, what is the value of X? The answer is 3. Now, if I put the number 3 back in the bag, and I say, what's the value of X now? The value of X right now, it has no value. Again, it's sitting there waiting for you to draw a number. Then I go and draw another number. I draw the number 1. Now the value of X is 1. So the value of X is just the current number that I've drawn out of the bag. If I put it back in, right now the value of X, no value. It's waiting for me to draw. If I draw again, let's say I get the number 3 this time, now the value of X is 3. If I put the number 3 back in the bag right now, what's the value of X? has no value. Okay, then I draw another number. I draw the number 4. Now the value of x is 4. Okay, let's go and so those numbers, if you care about, again, so I'm just saying it again, if you care about where do these numbers come from, or what do those numbers mean, the numbers you just saw, 3, 1, 3, 4, those numbers came from some experiments whose outcomes we changed to numbers. What could it have been? And do we even care about the experiment whose outcomes we changed to numbers? If we need to know what the original experiment is, whose outcomes we changed to numbers, then we'll mention it. If we don't need it, then we won't mention it. So for example, the problem could have said, we're going to draw a number out of, we're going to draw a card out of a deck of cards. We have a deck of cards, we're going to draw a card, and we're going to bet on what card comes out. And when you saw those numbers could be the amount of money you win when you draw the card. So when I saw the 3, that 3 could mean I just won $3. And you'll say, well, how did you win $3? Well, I'm betting with a friend. So here's the background information, right? I'm betting with a friend. I drew a card out, and the card that came out was one of those where I win $3. When you saw the 1, it means I drew another card out of the deck. At that card, I won $1. When you saw the 4, maybe it meant I won $4. I'm just giving an example of what the experiment could be, okay? And again, in most problems, I'm not even going to mention the experiment in the background, but if we need to know it, then someone will tell you. Well, first we had this experiment, and then we changed the names to numbers. Okay, so the experiment in the background could be betting on the draw of a card from a deck of cards. So that's what those numbers could have meant. Or I'll give you a second example of what the experiment could have been. Maybe we were flipping a coin 4 times, and the number that you saw was the number of times the coin landed on heads. So when you saw 3, that meant we flipped the coin 4 times. It landed on heads 3 times. So the 3 means it landed on heads a total of 3 times. When we saw the 1, it meant the coin landed on heads a total of 1 time out of the 4 flips that we made. When you saw the 4, it could mean the coin landed on heads 4 times. We flipped the coin 4 times, and it landed on heads all 4 times. So remember, ultimately, a random variable is a bag of numbers, but it comes from some experiment. Every probability problem has an experiment, and we relabel the outcomes. We change the name of the outcomes to numbers, and that's what the numbers in the bag are. So numbers in the bag could have been the total when you flip a coin 4 times, total number of head symbols when you flip a coin 4 times, or it could have been something else. So I'm just making up some examples of what those numbers could have come from. So they come from somewhere, from some experiment. Okay, but let me say it one more time. When you have a random variable, the minimum you need to think about is bag of numbers, and we're going to draw ones from the bag. What do the numbers mean? Okay, a little more to the story if you care about what the numbers mean. And if you don't care about what the numbers mean, then we just have bag of numbers. We're drawing ones from the bag. Okay, and then if you know the probability distribution, so I mentioned it already, I'm going to mention it again. If you know the probability distribution of your random variable, let's say the probability distribution for this bag is this. Normally I make it a 2-column table. This time I made it a 2-row table because I was going to run out of room if I made 2 columns on my slide here. So it's 2 rows. But anyway, once you know the probability distribution, you know a lot about the numbers in the bag. For example, the first row here tells me all the different numbers in the bag. So this tells me the bag has 0s, 1s, 2s, 3s, and 4s in it. When I was drawing a minute ago, we saw 1, we saw 3, and we saw 4. But we never got a 0 and a 2. But now that I know the probability distribution, I know there's some 0s in there and there's some 2s in there. And I probably have to draw a bunch more times before I see those, okay? But now I know exactly what numbers are in the bag. So 0, 1, 2, 3, and 4 are in the bag. And I know the probability of drawing those numbers out of the bag. And when you look at these probabilities, no wonder we didn't see the number 0. It's only got a 5% chance. There's not a lot of 0s in the bag. Yeah, eventually I'll get one if I keep drawing, okay? But there's not a lot of them, so it's hard to get, kind of thing. Whereas, you know, when we were drawing, you saw the number 3 twice. The reason is because 50% of the numbers in the bag are 3s. There's a lot of 3s in the bag. That's the idea. So you know all the numbers that are in the bag. When you know the probability distribution, you know all the numbers that are in the bag and the probabilities of drawing those numbers. That's what it says over here. So then I know the possible numbers that can be drawn out of the bag. I know the probabilities of drawing those various numbers from the bag. And we also know 3 other things because we talked about in section 6.1 that if you know the probability distribution, then you can find the average, standard deviation, and variance of all these numbers. The average, we called it the expected value. So we also know the average, standard deviation, and variance of all the numbers in the bag. So again, once you know the probability distribution, you know pretty much anything you would really care about as far as the numbers in the bag. All right. So that's just like a quick recap of what a random variable is and some stuff we did in section 6.1. Now we have to talk about what's the difference between a continuous random variable and a discrete random variable. What's the difference? All right. So this is the wrong answer. I'm going to give you a wrong answer first. Hopefully that doesn't confuse anyone. Sometimes students think that discrete random variable means there's only a finite amount of numbers in the bag, and continuous means there's an infinite amount of numbers in the bag. That's wrong. Okay. Like if your bag only had 1, 2, and 7 in there, that would be discrete. If your bag had, you know, all real numbers. Let me not just write all decimals. That would be continuous. So this is actually correct what I have, but if you look here, there's only 3 numbers in the bag. That makes it discrete. That's actually true. There's an infinite number of numbers in the bag here, all decimals. Any decimal, any number you can think of is in the bag. That's an infinite amount of numbers. You might say, Greg, I can't make a bag with an infinite amount of numbers. You're right, but we can still think about it. We can still imagine we have a bag with all decimals in there, and that would be continuous. But in my example here, there's only a finite amount of numbers here, and it's discrete, and there's an infinite amount of numbers here that's continuous, but that's not what it means. Okay, so in other words, you can have a discrete random variable where there's infinite. So it could be finite. You can have a finite amount of numbers, or you can have an infinite amount of numbers in the bag, and it can still be discrete. Continuous is always infinite. So anyway, just don't think discrete, finite, continuous, infinite. That's wrong. What it means, what is really the difference between continuous and discrete? It has to do with, well, gaps is really the right answer. It has to do with gaps. But let me say it like this. Let's say you have a bag of numbers, and you're going to make a picture. You're going to draw a picture of all the numbers that are in the bag. Okay, so let me just give you a quick, we're going to look through more examples, but as far as discrete goes, so here's a number line, okay? And let's say you're going to put a dot at all the numbers that are in the bag. Let's say the bag has 3s, 5s, 8s, and that's it. There might be many 3s, many 5s, many 8s, or just 1 3, 1 5, 1 8. I don't know. But the bag has 3s, 5s, and 8s in it, and that's it. In other words, all the different numbers in the bag, you put a dot on the number line. Okay? If your picture looks like this, when I say looks like this, I mean if it looks like a bunch of dots with gaps in between, this is a gap. Okay? Meaning there's 3s in the bag, there's 5s in the bag, but there's no number between 3 and 5 in the bag. That's a gap between 3 and 5. There's nothing between 3 and 5 in the bag. Same thing here. There's 5s in the bag, there's 8s in the bag, but there's nothing between 5 and 8 in the bag. That's what I'm calling a gap, or a jump, if you want to call it a jump. If you draw a picture of all the different numbers in the bag, draw it on a number line, and you get a bunch of dots with gaps in between, that makes it discrete. Sometimes when I explain this, so I guess I'll just say it now. So if I draw the number line in red, not red, in blue, think of this as like a river. That's why I'm making it blue, okay? And then there are some rocks, okay, in the river. So there's a rock here. There's rocks at the numbers that are in the bag. There's a rock at 3, there's a rock at 5, and there's a rock at 8. If you were standing here, okay, that's me trying to draw a person, okay? So you're standing at the number 3. If you want to get to the other spots without falling in the water, you have to jump. You have to make a jump to 5, you have to make a jump to 8. You can't just walk. Like, I can't blindfold you and have you walk. You'll walk and you'll fall in the river. That's it. So if there are those gaps where you fall in the river, that makes it discrete. Whereas continuous, what's the difference between this and continuous? Again, it all has to do with making a picture of all the numbers that are in the bag. So if you draw a number line, and if I say the numbers in the bag are every number between 3 and 8, I'm talking about not just 3, 5, and 8, not just the whole numbers, not 3, 4, 5, 6, 7, 8. Any decimal you can think of between 3 and 8. So 3.1, 3.107, 4.985, 7.2618, whatever. Any decimal you can think of between 3 and 8, then the picture would look like this. You wouldn't even see any dots because the entire space between 3 and 8 is covered. Every number between 3 and 8 is in the bag. That's a continuous random variable. Yes, there's definitely infinitely many numbers here, okay, but it's not just that it's infinite. It's basically there's no gaps, no jumps. If you were standing at some spot on here, you could walk to another spot blindfolded. You wouldn't have to do any jumps. No matter how long or short your step size is, you can just walk without falling in the river, kind of thing. That's what a continuous random variable is. Let me say the whole thing one more time. A discrete random variable. A random variable is discrete. Again, when I say random variable, you're thinking bag of numbers, right? A random variable is discrete if you make a picture of all the numbers in the bag, meaning you draw a number line and you put a dot at all the different numbers in the bag. If you get a bunch of dots with gaps in between, then that's a discrete random variable. Whereas for continuous random variable, again, same thing. You make the picture, you draw a number line, and you put a dot at all the numbers that are in the bag. Those dots are going to bleed into each other because it's all numbers between 3 and 8 in this example. If it looks like a range of values with no gaps, that makes it a continuous random variable. Okay, I'll say all that one more time. Let's click through this here. So discrete random variable, the possible values of x are finite or countably infinite. So there could be infinitely many numbers in the bag. I'll show you in a second here. So here's a quick discrete random variable. Okay, so again, what I'm trying to say in this picture here, I'm drawing a picture of all the numbers that are in the bag. There's a number line. I have a dot at every number in the bag. And what I'm trying to say is the bag has 3s, 6s, and 8s in it, and that's it. And again, I don't mean 1, 3, 1, 6, 1, 8. There could be many 3s. There could be infinitely many 3s. Okay, just how many different, put a dot at all the different numbers. So you get a dot at 3, a dot at 6, a dot at 8. That's it. So if you were to draw out of this bag, you can draw 3s, 6s, and 8s, and that's it. When you look at this picture, it's a bunch of dots with gaps in between. So there's a gap right here between 3 and 6. There's another gap here between 6 and 8. That makes it a discrete random variable if it has gaps. Here's another one. So imagine a bag of numbers, and I draw a picture of all the numbers in the bag. I draw a number line. I put a dot at every number that's in the bag. And what I'm trying to say here is, what are the numbers in the bag? Well, 3, 4, 5, 6, 7, 8, 9. This dot, dot, dot means it keeps going. So then it goes 10, 11, 12, 13. There's a dot at each one of those numbers. You go back the other way, there's dots over here as well. So there's a dot at 2, a dot at 1, a dot at 0, a dot at -1, a dot at -2. Basically, there's a dot at every integer, okay? Even if it's negative, positive or negative integer. Basically means whole number, but it could be negative, okay? There's a dot at every integer. The possible values are all integers. There's infinitely many dots here, right? So again, it could be finite or it could be infinite, okay, for a discrete random variable. But what's the deal? If you look at this picture, there are gaps. Like there's a gap there between 4 and 5, meaning the number 4 is in the bag, the number 5 is in the bag, but nothing between 4 and 5 is in the bag. Like 4.7, 4.28, those numbers are not in the bag. That makes it a discrete random variable. So one more time, let me say that. If you draw a picture of all possible values of your variable, if it looks like a bunch of dots with gaps in between, that makes it discrete. Continuous random variable, the definition is the possible values of x contain an interval. Here's a quick example here. What I'm trying to say is you have a bag of numbers. And what numbers are in the bag? All decimals between 5 and 8. So when I draw a picture like this, it's every number you can think of between 5 and 8. Not just 5, 6, 7, 8. Not just the whole numbers. Any decimal. 5.27, 6.18492, you know, 7.00159. Any number you can think of between 5 and 8. So if you draw a picture of all possible values of your variable, and it looks like a range of values with no gaps like this, then it's a continuous random variable. So here I'm trying to say we have a bag of numbers and the numbers are all, we should be writing all decimals between 5 and 8. Here is another example of a continuous random variable. Again, what am I doing? I'm drawing a picture of all the numbers in the bag. So you draw a number line, you put a dot at all the different numbers in the bag, and here the entire number line is painted, meaning every single number, every single decimal is in the bag. So the positive values of x here, the positive values of your variable are all real numbers, are all decimals. And again, that's continuous because, again, you don't see any gaps. There's every number imaginable in there. There's no gaps in between where those numbers are not in there. That makes it continuous. Okay. One last thing to say, sometimes students think, oh, discrete means whole numbers and continuous means decimals. That's not correct either, because let me just give you one quick example. A person's shoe size is an example of a discrete random variable. Let's go and take a look at the shoe size. Like what can a person's shoe size be? It could be like 9, it could be 9.5, it could be 10, 10.5. There's other ones, but let me just put those 4 for now. And again, if you look at shoe sizes, it's a bunch of dots. If you draw a picture of all possible shoe sizes, it's a bunch of dots, but there's still gaps because you can have a shoe size of 9 or 9.5, but you can't have a shoe size of 9.3 or something like that. So shoe size is an example of a discrete random variable, but there are decimals. You see like 9.5, okay? So that's the idea. All right. So when your bag of numbers, when your random variable is discrete, there's one way of handling those problems, and we talked about how to do that in chapter 6. Now we're talking about continuous random variables. Things have to change now. Like, how do we deal with continuous random variables? How do we do the things we did in chapter 6, like find the probability distribution, find probabilities of certain things, find expected value, standard deviation, variance, all these things? How do we do those kinds of things when it's a continuous random variable instead of a discrete random variable? So here's the deal. Things are going to change in chapter 7. We want to keep as much as possible that we had before in chapter 6. Want to keep as much as possible, but some things are going to have to change. So let's go and see, how do we handle continuous random variables? Actually, to tell you the truth, it's not very hard, but it is different than what we did in chapter 6. So for a continuous random variable, a probability distribution is a curve. Okay, this is very important. In chapter 6, last chapter, a probability distribution is a table. But that's for a discrete random variable. In chapter 7, a discrete random variable is no longer a table, it's a curve. I'm talking about a curve like if you've ever, graphed like a parabola, like y equal x squared or something, something like that. That's a curve. Okay. So a probability distribution is a curve. You're gonna have some kind of curve. It might not look like that. It might look, who knows what it's gonna look like. But whatever the curve is, that curve is gonna give me pretty much the same information as the table gave me in chapter 6. Okay, but it's a curve. It has to be a curve because, for example, you can't make a table because what are you supposed to put in the left column of the table? You're supposed to put all the different numbers in the bag. Well, there's going to be infinite many numbers in the bag. You can't make the whole table. It would go on forever. So things have to change. So one thing, probability distribution becomes a curve. There's actually 3 names for this curve. It could be called a probability distribution. Sometimes it's called a density curve. Sometimes it's called a probability density. So whatever. Anyway, different names for this curve. But again, for a continuous random variable, a probability distribution is a curve. The possible values of x, if I want to know what are all the numbers in the bag, it's all the numbers on the x-axis for which there's a curve above them. We'll talk about it when we do an example. But it's all the numbers below the curve, basically, that are on the x-axis. Okay, here's the next one. Probabilities are areas. In chapter 6, when you're trying to find probabilities, in section 6.1, we did something. In section 6.2, we did something. But in chapter 7, today, when you're trying to find a probability, you're going to be finding an area. What am I talking about, area? You ever found an area of a circle or area of a square, or area of a rectangle, these kind of things? That's what I'm talking about. You're going to find an area. Whenever I ask you to find a probability, you're going to find an area. Or if you found an area, you found a probability. When I say area, let me be more specific. What we're going to be doing is we're going to find the probability of something, we have to find the area under the curve, above the x-axis, and between the two numbers that are given. Most of the time in problems, two numbers are going to be given. You're going to find the number, again, it's the area below. So under the curve, above the x-axis, between the numbers that are given. If you have no clue what I'm talking about, I understand. As soon as we see an example, it'll make more sense. Okay, before we see an example, we're going to go over just a couple quick things. The requirements for a probability distribution for a continuous random variable. In chapter 6, we had two requirements for a probability distribution for a discrete random variable. The first one was, remember, for a discrete random variable, chapter 6, probability distribution was a table. There were two requirements on this column, the probability column. First of all of these had to be between 0 and 1. And if you add them all up, it has to add to 1. That was for chapter 6 kind of random variable. For chapter 7 random variable, we don't have a table anymore. We have a curve instead. Okay. We're still going to have two requirements for a probability distribution for a continuous random variable. We have two requirements on the curve. Okay. The first requirement is the curve must be above or on the x-axis. The curve cannot go below the x-axis. I want you to think about it like this. Think about it as if the curve went below the x-axis, then we could get a negative area, okay? And probabilities can't be negative, areas can't be negative, but if the curve could go below, we can get a negative answer for a probability. We can't get a negative answer for a probability, so the curve has to be above or on the x-axis. In other words, it could touch the x-axis, so you can have an x-axis and some kind of curve. It could touch, but it can't ever go below. Okay, that's the idea. The second requirement is, if you find, remember, probabilities are areas. So find the area under the curve, you're going to get a probability. I'm trying to do the requirement that's analogous to the total of all the probabilities is 1. So for discrete random variable, the second requirement was total of all the probabilities on the right side of the table is 1. For continuous random variable, it's the area under the whole curve has to be 1. That's the second requirement. The area under the entire curve must be 1. Now, when I ask you this on the next quiz, and I say question 1, state the requirements for a probability distribution for a discrete random variable. I'm very picky on this one. Okay. If you write the area under the curve is 1, you're not going to get credit because every probability is an area under the curve. The area under which part of the curve is 1, the area under the entire curve, that's why I have entire written underlined. You don't have to write the word entire, but you got to write something like that. Area under the entire curve, area under the whole curve, something like that. The area under everything has to be 1. Okay, those are the two requirements. All right, let's move on. So I'm going to just summarize what I just said, and then we'll do a bunch of examples. Okay, so this is comparing discrete and continuous random variables. Okay, so the probability distribution. So I want you guys to help me out with the answers here, okay? For a discrete random variable, the probability distribution is what? So for discrete, for chapter 6 random variable, what kind of thing is the probability distribution?
Table.
It's a table, that's right. But in chapter 7, it's not going to be a table. In chapter 7, the probability distribution is a
curve.
It's a curve, that's right. All right, next. When you're trying to find probabilities, when you're dealing with random variables and trying to find probabilities, for a discrete random variable, what I told you in order to find probabilities is you go back to the sample space, or you go back to the original experiment to figure out the probabilities. That's what we learned how to do last class in section 6.1. For a continuous random variable, stuff we're going to be doing today, when you're trying to calculate probabilities, you're going to be finding an area. Okay, so that's our job. Area under the curve. You're going to have to find some kind of area under the curve. Okay, so that's the difference for there. And then we have the two requirements for probability distribution. The first one, for a discrete random variable, again, the one where you have a table, the first requirement for the probability distribution is all the probabilities on the right side of the table have to be what?
Equal to 1?
No. Okay, so you might be getting confused with the second requirement. Every single probability has to be what?
Positive.
Okay, positive, and what else?
0 and 1.
Has to be between 0 and 1. Okay, that's what this says right here. All the probabilities on the right side of the table have to be between 0 and 1. The analogous requirement for the curve is the curve has to be what?
Above the x-axis.
Above the x-axis. On or above. It can touch the x-axis or above. Or you can write the curve cannot go below the x-axis, something like that. Let's go to the second requirement. For a discrete random variable, the second requirement is if you add all the probabilities on the right side of the table, you get what? If you add them all up,
You get 1.
you get 1, right? Okay, that's for a discrete random variable. For a continuous random variable, that translates to if you find the area under, finish my sentence, area under what?
The area under the curve.
Area under the curve will not get you credit.
Area under the curve equals 1.
Area under the curve equals 1 will not give you credit.
The area under the entire curve equals 1.
Area under the entire curve or area under the whole curve, something like that, has to be 1. Okay, make sure that's clear. Because again, every probability is an area. But which one has to be 1? The area under the entire curve has to equal 1. Okay, now we'll do some examples. Any questions so far? Okay, so let's go ahead and look at this example here. Example 1, let x be a random variable with the following density curve. So we have this density curve over here. So I'm giving you, so in this example, I'm giving you a curve. And I want to make sure we just understand what is being conveyed to you. So I want to answer some questions now about our random variable. Remember, every time I say random variable, what are you thinking? Tell me what you're thinking. When I say random variable, you think of what?
Numbers.
You think of a bag of numbers. We have a bag of numbers and we're going to draw one number from the bag. And this is communicating everything I would want to know about that bag of numbers, but we have to extract the information. And now I have all these questions. Like part A says, what are all the possible values of x? I'm asking, what are all the numbers you can get out of the bag? Okay. And then I'm asking, what's the probability of getting certain things out of the bag? All right. So we'll do all that. Let me make this a little bit smaller. Okay. Part A, what are all possible values of x? Okay. So students get this one wrong often. So let me just tell you the wrong answer, and then I'll tell you the right answer. You're supposed to look at the x-axis, the number line that's on the bottom there, okay? And when you look there, you see the number -9, 4, 18, and 24. And someone will say, when asked for what are all possible values of x, again, I'm asking what are all the numbers in the bag? Students will say -9, 4, 18, and 24 are the numbers in the bag. And they're wrong, because if you thought it was just -9, 4, 18, and 24, and that's it, this would be a discrete random variable. You see there's a bunch of dots with gaps. This is not a discrete random variable. It's not just those 4 numbers that are labeled. But the reason I labeled those 4 numbers is I'm going to ask you questions later on involving those numbers. When you're trying to find all possible values of x, here's what you have to do. I want you to imagine that this curve that's drawn in red over here falls straight down to the x-axis. It just falls down. If you imagine like this point on the curve falls down, hits here. This point falls down, hits here. If the entire curve just falls straight down, which part of the x-axis would it cover? It would cover all of this. That's basically all the numbers under the curve. If you took the curve and went straight down, or these are all the numbers that have a curve above them. Like this number over here, there's no curve above it. Okay, this number here, no curve. But this number over here, there's a portion of the curve above it. This number here, portion of the curve above it. But I think the easiest way to do is just imagine the curve just falling straight down to the x-axis. And now what numbers are covered? All numbers, not just -9, 4, 18, 24, but any number you can think of between -9 and 24. And this is how I want you to write it. Everyone pay attention to how I want you to write it. I want you to write all decimals. Get the word decimals in there because it makes it clear. all decimals between -9 and 24. Any decimal, any number you can think of between -9 and 24, that's what's in the bag in this problem. So we got a bag of numbers, and this is telling me what numbers are in the bag, all decimals between -9 and 24. Any questions? All right. So now we're going to ask some probability questions. We've seen this notation once before, but we need to make sure we really understand it now. Whenever you see, this is how the notation, when you want to write between, okay? What you do is you put the variable in the middle, you put the smaller number on the left, put the bigger number on the right, and you have to put two less thans. These have to both be less thans. Sometimes I see students put a less than on one side, and they'll put like a greater than on the other side. This makes no sense, okay? In mathematics, for it to be written correctly, you got to put x, you have to put two less thans, and 9 and 12. And then let's say it was 9 and 12. Then this is me asking you, if you were to draw a number out of the bag, what's the probability to get a number between 9 and 12? Let's go ahead and look at the part B. Again, when you see this notation, remember we have a bag of numbers, and this is what I'm asking. If you draw one number out of the bag, because that's what we're doing, what is the probability the number you get, that's x, the number you get, is between 18 and 24. So that's what I'm asking. And most probability questions involving continuous random variables will be like that. Let's probably get a number between two things. Okay, so let me say the question one more time, and then I'll show you how to get the answer. So the question is, remember we have a bag of numbers. We're going to put our hand in the bag and draw a number. What's the probability we end up with a number between 18 and 24? That's the question. Now to get the answer, this is what you do. You locate the number 18 on the number line, here it is. Go from there up to the curve. Then you locate the number 24, the other number, go from there up to the curve. And now you're going to shade an area. And by the way, when I'm grading, I'm looking to see if you shaded the area. Please make sure you shade the area. I'm going to shade an area below the curve. Below what? Someone tell me, below what? Just below the curve, above the x-axis, above what?
The x-axis.
The x-axis, and between the two blue lines I just drew. So we got to go below the curve, above. So this is the x-axis. So below the curve, above the x-axis, between these two lines. I'm talking about this area here. I'm going to be wanting you to shade this on the quiz and on exam 2, so please don't forget to do it. So you shade this area. This area that I'm shading in blue right now is this probability. And the number's given to you in this problem, so you just have to read the answer now. What's the answer?
0.15?
Yeah, 0.15. That's it. Okay, so you just have to go, okay, let's look at the picture. Let's find the area we have to find. If you're trying to find a probability, you got to find an area. And in this problem, I'm giving you the area. You just have to go, oh, there it is, 0.15. Now, you don't have to do what I'm about to do. I'm going to change it to a percentage. The reason I'm going to change it to a percentage is because in a minute, I'm going to ask you to explain the meaning of these probabilities. If I don't ask you to explain the meaning, then you can write the probability any way you want. A decimal, fraction. I mean, you could just write 0.15 and stop. But I'm writing 15% just because I'm going to ask you to explain the meaning of this in a couple minutes. Okay, that's part B. Let's go to part C. Again, there's a bag of numbers somewhere. And I'm saying, if you were to put your hand in the bag and draw a number out, what's the probability that the number you get is between 4 and 24? What's the probability you end up with a number between 4 and 24? That's what I'm asking. Okay, so now how do you find this probability? Let's erase this. And I'm going to go ahead and shade again. If you were doing this on a quiz or an exam, I guess you'd have to redraw the picture. But usually I only ask you one, so you don't have to redraw the picture. But for this problem, you would have to just draw it a few times. But okay, how do you find this probability? Remember, to find a probability, you're going to find an area. So here's how you find it. You start with the number 4, locate that number on the x-axis, and go up to the curve. Okay. Then look at the other number, 24, locate that number on the x-axis. Here it is. Go up to the curve. And then you're going to shade an area. The area is going to be below what? Below the what?
The curve from 4 to 24.
Yeah, it's going to be below this portion of the curve. So we're going below this. It's going to be above what?
The x-axis.
Above this portion of the x-axis. And between the two blue lines that I drew. So we got to find that area. First, make sure you shade it. I'm looking for you shading it on the quiz. Don't forget to shade it. So just in this entire area over here, below the curve, above the x-axis, between the two blue lines. Anyway, so that area there is what we need to find. Now that we know what, so this probability is the blue shaded area that I have over here. And now you just give me the answer. And you can just read, again, the areas are given to you in the picture. So you just read them off. Well, what is it? Tell me. What is the area?
0.66.
Okay, how did you get it?
I added 0.51 and 0.15.
Right. We'll go ahead and write that down. So the answer is 0.66. And again, you can leave the answer like that unless I ask you to explain the meaning, which in this problem I will. So I'm going to change it to 1% so we can explain the meaning later. Okay, that's part C. Any questions on part C? Okay, let's go to part D. It's another one like these. Again, we have a continuous random variable. You're thinking bag of numbers, and I'm saying, and we're going to draw one number out of the bag. Every time I say random variable, that's what you think. Bag of numbers, we're going to draw one out of the bag. And I want to know what's the probability I get a number between -13 and 18. Again, that's how you write between. Probability that the number I get when I draw one is between -13 and 18. So here's how you can do this. Let's erase this part here. Well, you see there's already a problem. What you're supposed to do is you're supposed to locate the number -13 on the number line. It's not labeled there. If you were to extend the number line this way, then -13 would be, I don't know, maybe here. And so if I ask you, what's the probability of getting the number -13 out of this bag? The answer is there's no chance of getting the number -13 because there's no curve above the number -13. -13 is not in the bag. Okay, so whenever they do that to you, well, actually, let me do this first. So we're trying to figure out the probability of getting a number out of the bag between -13 and 18. But -13 is not in the bag, so it has no chance of coming out. And actually, none of these numbers between -13 and -9 can be drawn out of the bag. None of them are possible. Those numbers are not in the bag. They're not in the bag. Why? Because there's no curve above them. So all these numbers right here that I'm shading, none of those numbers are in the bag. So that part of the number line, we are going to throw it out. What you're going to do in this problem is you have to rewrite the question. Here's the question. Probability to get a number between -13 and 18. That's the same as the probability that we get a number out of the bag between, I need you to throw out this part. Okay, so probably we get a number between there and there. The same as the probability we get a number, I want you to throw out this part and tell me what the answer is. Probability we get a number between what and what?
-9 and 18.
-9 and 18. Please don't forget to rewrite the problem. If the number goes beyond the curve, I need you to rewrite the problem. When we do example 2, that becomes even more important because you can get the wrong answer if you don't rewrite it. All right, everybody with me so far? So again, the probability of getting a number between -13 and 18 is the same as probably getting a number between -9 and 18 because we threw out this part. That's the only difference. We threw out that part, but that has no chance of happening because those numbers are not in the bag. Okay, so you rewrite the problem first. Okay, now that we've done that, now how do you find this probability? Well, you're going to locate the number -9. Here it is. I would say go up to the curve, but you're already on the curve for that one, so just stay there, okay? Locate the number 18 and go up to the curve. And then you draw, as you shade an area below what? Below the what?
The curve.
Yeah. below this portion of the curve. Okay, so so we're trying to find the area below the curve above what?
The x-axis.
Above the x-axis, above this portion of the x-axis. Okay, and between this blue line over here and this dot over here. Okay, so we're just going to shade that region over there. Just shade it. So you're going to shade this entire area here, and then you're going to figure out what the area is. Again, they're labeled there. You're just going to have to figure it out. So tell me what to do now.
We calculate the area. So
But
0.34 plus 0.51.
yeah, add those up, 0.85. And again, you can leave the answer like that, but I'm going to change it to a percent just because we're going to explain the meaning in a minute. That's part D. Any questions on part D? Okay, and then let's go to part E. Probably x equal 4. So I want you to notice that B, C, and D, they all asked, what's the probability to get a number between here and here? Okay, but now part E is not asking that. It's saying, what's the probability to get the number 4? So again, remember, we have got a bag of numbers. We're going to draw one number out of the bag. What's the probability to get the number 4? That's the question. What's the probability I draw the number 4 out of the bag? 4 is in the bag. You see over here, 4 is in the bag. What's the probability I draw the number 4? The answer is 0. If you write it as a percent, it's 0%. Now, let's talk, because this one's going to be confusing. So I'm going to try my best to make it to lower the confusion level here. By saying a few things. First of all, I'm going to say this first. Before I explain why it's 0, I'm going to tell you this. When it's a continuous random variable, and it's only for continuous, only chapter 7 kind of random variables, not chapter 6 kind of random variables, but only for a continuous random variable, if you get a problem where it says probability x equals one number, so if inside the parentheses, it's just x equals one number and that's it, the answer is always 0. I don't care what number it is. It's always 0. Okay? Probability x equals 10, 0. Probability x equals 18, 0. Probability x equals 12, 0. It's always 0. Okay? So if it's x equal a number in the parentheses, it's going to be 0 always. So memorize that. That's the first thing. But again, that's only for continuous. On the quiz today, you had problems like this, but the answer wasn't 0. You had to use some formula or whatever. But if it's continuous, only for continuous, the answer is always 0. Okay, so memorize that. Next thing, why I want to explain for a minute why it should be 0. Because 0% probability before in chapter 6 meant it has no chance of happening. But it has to have a chance, right? Like, I mean, 4 is in the bag, it can come out. Okay, so how come we're getting 0? So one thing I mentioned to you was in chapter 7, things are a little different than things that we had back in chapter 6 and chapter 5. Some things are going to change. And one thing that's going to change is 0% probability doesn't exactly mean that it's got no chance of coming out. Okay, but you have to understand things are weird because it's a continuous variable. That means we have a super huge, infinite amount of numbers in the bag. So just things are a little bit weird. So it's a little weird. I get it. 4 is in the bag, but what's the probability getting the number 4? 0. I get it's weird. Here's 2 ways to see why 0 makes a little bit of sense. One reason is, you know how hard it is to get exactly the number 4 out of the bag? I mean, think about it. There's so many numbers in the bag. Let's say you put your hand in the bag and you said, and you draw a number out and you say, hey, Greg, look, I got the number 4. I'll look at your number and I'll go, let's see, did you get exactly 4? Because what does 4 mean? It means 4.000000000 is the rest of the way. Maybe the number you got out of the bag was 4.000052819. Maybe there's some other digits there. You get what I'm saying? It's super close to 4, but it's not 4. Or you got 4.000000000, then 1836. because there's so many numbers in the bag, it's so unbelievably hard to get exactly the number 4. So that's one reason to say that the probability is 0. That's my first explanation. If you didn't like that, I'm going to give you a second one. Second explanation, I want you to remember that probabilities are areas. And the only way you can find an area is if you basically have to have like, a region to find an area between. Okay, so when they say find the probability that x equals 4, like, let me back up. In part B, it said between 18 and 24, so we had some region in between to find an area of. But when it says 4, it's like we're finding the area between the number 4 and the number 4. But the two lines are drawn in the same spot. It's not like we have a line and another line, so we have something to find the area of. So between 4 and 4, it's kind of like we're trying to find the area of this line. And lines don't have an area, okay? The area of a line is 0, okay? You have to have, again, the lines have to be in like 2 different spots for there to be some kind of space in between to find the area of. So that's another reason why the probability is 0. Now, if you didn't like either, those are the only 2 explanations you're going to get. If you don't like any of my reasons why the answer should be 0, well, at least memorize that it's 0 when it's a continuous random variable. One more time. Only for continuous random variable. If it says probability x equals one specific number, the answer is always 0. All right, any questions? Okay, so we have to explain the meanings of these probabilities. So part F says, explain the meaning of the probabilities found in parts B through E. Okay, I'm going to write down the first one, and then I'm just going to say the rest of them. The first one, part B, probability that we draw a number between 18 and 24. This probability was 15%. I'll write this one out. What does this probability mean? Now, when you're trying to write down what a probability means, you're supposed to say if you do something many times. What are we doing? We have a bag of numbers and we're drawing a number out of the bag. That's what we're doing. Bag of numbers, we're drawing one number out of the bag. If we do that many times, so the way you would say it, I guess to be a little more clear, what I want you to say is, if you draw a number out of the bag that has this probability distribution, this meaning this curve here is letting me know what the probability distribution is. If you draw a number out of the bag that has this probability distribution many times, you're going to get a number between 18 and 24 about 15% of the time. Remember, the event is what's in parentheses, and this is the probability over here. Let me go ahead and write all that down. So if you draw a number out of the bag with this probability distribution. And when I say this, I mean the curve up there. Okay. If you draw a number out of the bag with this probability distribution many times, the number will be between 18 and 24 about 15% of the time. Okay, so this will happen. The number you get will be between 18 and 24 about this percent of the time. Okay, so that's how you write that answer. I'll leave it on the slide a couple seconds in case anyone's copying it. But then I want you guys to help me to say the answers to the other ones. So let me wait just a couple seconds here. Okay, so let's go to the other ones. All right, so I want someone to help me explain the meaning of the 66% over here. And just follow the format of that last one. Someone try it.
If you were to draw a random number from a bag of numbers with this probability distribution, you would draw a number between 4 and 24 about 66% of the time?
Exactly, yeah. All right, someone try to do part D.
If you draw a number out of the bag with this probability distribution many times, the number will be between -9 and 18 inclusive about 85% of the time.
Yes. Let me say a couple things though. You don't need to say inclusive, even though you're technically correct on the inclusive part, but you don't have to say it. But also, when you said the answer, you said -9 and 18, which is fine, but I would prefer, and I wouldn't take off points, but I'm just letting you know, I would prefer you use the numbers that are in the question before we rewrote it, because that was what the question asked you. Okay, so I would just say -13 and 18 instead of -9 and 18. But again, it's not that big a deal. All right, let me go ahead and do part E for you because E is a little bit weird. So you say basically the same as the other ones. It would go like this. So this one here. If you draw a number out of the bag that has this probability distribution many times, you'll get the number 4. Instead of saying you'll get a number between here and here, you just say you'll get the number 4 about 0% of the time. And we'll just leave it like that. Okay, questions?
Would you like us to say with or without replacement?
You don't need to, but yes, it is with replacements.
These probability statements, they will never not be inclusive, correct? Or they might be.
So we're getting a little, I didn't really want to mention this until tomorrow, but yeah, okay. So if I get rid of the equal signs, like over here, if I wrote probability X is between 18 and 24, and I don't put the equal signs, technically the correct way to say it is exclusive, whereas this would be inclusive, this would be exclusive.
Right.
And for a discrete random variable, this would be a big deal, like the stuff we did last class. But for continuous random variables, the answers to these are going to be exactly the same.
Because the equals 4 is 0, or the equals blank is 0.
When it's equal one number, it's just 0. So you can get sloppy about inclusive, exclusive when you have continuous random variables because the answer is going to be the same either way.
Gotcha. Okay, that makes sense.
Yeah. So that's the idea. You can say inclusive, which is technically correct, but if you said you didn't, it's fine. And if you didn't put the less than or equal to and you just put less than, that's fine for continuous random variables only. Okay, so one last thing I want to do here, and then we'll go to the next example. I want to check the 2 requirements for a continuous random variable. The first requirement was that the curve has to always be above or on the x-axis, and you can see that's the case. The curve is above the x-axis here. It does touch it here, but it never goes below. Okay, so the first requirement is satisfied. The second requirement is that the area under the entire curve, that means starting at -9 and ending at 24, the area under the entire curve is 1. And you can check that by adding. You could do 0.34 plus 0.51, that's 0.85, plus 0.15, that's 1. So the area under the whole thing has to be 1, and it is. So I just wanted to check that. All right, questions? Okay, so this first example, I drew the curve for you, and I said, okay, answer all these questions now from this curve that I've drawn. So now we're going to do a second one, but I'm not going to draw the curve this time. We're going to talk about one special curve. It's actually super easy one, the easiest one there is. It's called the uniform distribution. So on the quiz next time and on the next exam and so on, when we talk about uniform distributions, this kind of problem, I'm not going to draw the curve for you. You need to know what it looks like. Uniform distribution basically looks like a straight line. You know, when you say curve, you expect it to be curvy, but a line is, those are called curves as well in math. Okay? But uniform distribution is going to look like that. It's going to be a horizontal line. That's what you need to remember. Uniform distribution is a horizontal line. Let's go ahead and read this over here. What does it say? Uniform distribution over the interval AB. Okay. So what do you need to remember about the uniform distribution? The curve, the density curve, is a straight horizontal line over the interval A to B. So notice it's going to start at the number A on the x-axis. It's going to end at the number B. Otherwise, it's a horizontal line. And C will denote the height of the curve above the x-axis. Now, this one, I usually don't tell you on a quiz what C stands for. I'm telling you what it stands for now. Don't forget it for the quiz. If I ask you to find C, C is how high the curve is above the x-axis. Here's a picture. Every uniform distribution looks like this. They're going to give you this interval, and basically that's telling you where the curve starts, where the curve ends. Again, the curve is going to be a straight horizontal line, and its height is going to be the number c. It's just how high it is above the x-axis. Okay, so remember that. Uniform distribution, horizontal line. And here we go. Here's another example. It looks very similar to example 1, but notice I haven't drawn a curve for you this time. Let's see what it says. Suppose x has a uniform distribution over the interval 3 to 15. Again, we have a bag of numbers. We're talking about a random variable here. Bag of numbers. We're going to draw one number out of the bag. But I got to tell you, I want to tell you the probability distribution so we can answer questions. In the last problem, I gave you the curve and some numbers were in there and we can answer some questions. Now I'm saying it has a uniform distribution over the interval 3 to 15. That's all the information you need to answer questions involving this random variable. Part A says find the value of c that makes this a probability distribution, and then we're going to find answer some probability questions. Let's do C first. Find the value of c that makes this a probability distribution. Okay, so let me go ahead and draw this. By the way, the uniform distribution is the only one I ever draw where I draw an x-axis and a y-axis. So I draw a number line like this and another line, because I want to put the height on the y-axis. I don't know what it is right now. I'm going to call it C. The uniform distribution, it says over the numbers 3 to 15. So I'm put the number 3 here, put the number 15 here, put x somewhere in the middle here. But anyway, then you draw a number line that starts at 3. I'm sorry, number line. You draw a horizontal line starting at 3, ending at 15. Try to make it look like a line. Mine didn't look like a line there. Jeez. Okay, we'll get it. Whatever, close enough. Horizontal line starts at 3, ends at 15. It has to have height c. So c stands for the height. And now to find the value of c that makes this a probability distribution, we're going to go through the 2 requirements. The first requirement for probability distribution is the curve can be on or above the x-axis, can't go below. And as long as c ends up being a positive number, we're above the x-axis, so we don't need to worry so much about the first requirement. It's all about the second requirement. What was the second requirement? The second requirement for probability distribution is the area under the entire curve has to equal 1. So I'm going to go from the start of the curve, from 3 up to the curve, 15 up to the curve, and I'm going to shade below the whole curve above the x-axis between these lines. This area that I'm shading here has to equal 1. It's area under the, so I'm shading the area under the entire curve. This area has to equal 1. So now I'm going to write down the area under the entire curve has to equal 1. Okay, now if you look at the picture, what shape is that area in the picture? What's the shape? This area that
Rectangle.
it's a rectangle, yeah. So you're going to need to remember the formula for the area of a rectangle. That's the only one you need to remember. Does anyone know what it is? Area of a rectangle?
Base times height.
Yeah, it depends on who taught it to you, what book you used. Some people use base times height, and some people use length times width. Either of those is fine. I'm going to use base times height. I'm going to write base times height equals 1. The base times height in that picture equals 1. Now the base is the length of this green segment here. It's the length of the bottom here from 3 to 15. How long is that?
8.
Huh?
8 units.
8?
12.
Oh my God.
It's okay. 12. 12 is the answer. And in general, you subtract the numbers. 15 minus 3, 8. No, I said 8. 15 minus 3, 12. Okay, so everybody with me on this?
My bad.
No, it's all good. You get it though?
Yes.
Okay, and then the height is C. That's what we called C. C is the height. It's the length of this part here. That's what C is. And that has to equal 1. And now we got to do some algebra. This is the only algebra we're ever going to do in this entire class. And it's very simple algebra, but you got to solve that for C. Does anyone know how to solve it for C?
Don't we divide
Yeah, divide both sides by what?
by the 12?
By the 12, yeah. And we get C is equal to 1 over 12. Okay, that's the answer to part A. That is the correct height of the curve so that the area of the whole thing is equal to 1. Questions on part A? All right, now let's do these other ones. Part B, find the probability that x is between 3 and 7. Again, we have a bag of numbers. This is communicating some information about that bag. And I'm saying, what's the probability if you were to draw a number out of the bag, you get a number between 3 and 7. All right, what I'm going to have to do is I'm going to have to draw the picture over and over again for each one of these. That's a little bit annoying, but what am I going to do? So let's do it. So I'm starting off by putting the numbers 3 and 15. I know the problem has 3 and 7 in it, but I'm first going to draw a uniform distribution from 3 to 15. Now that I know the height, I'm going to put that in there. It's 1 over 12. So you draw a horizontal line from the number 3 to the number 15. Okay. Now that so every picture I draw is going to have this much in it. Now it says find the probability we get a number between 3 and 7. So what you do is you go from the number 3 up to the curve. Number 7 is not labeled, but it's somewhere between 3 and 15. It's like somewhere here. Let's say I'll put a 7. Go from there up to the curve. And then again, you shade below the curve, above the x-axis, and between those two blue lines. This area here is this probability. Remember, probabilities are areas. Okay, what is the shape of this area that's shaded? What's the shape of it? Anyone?
Also a rectangle?
It's also a rectangle. Actually, every area for a uniform distribution is going to be a rectangle. They're all going to be a rectangle. So this probability is base times height again, but it's base times height in this picture now instead of this picture. Okay. What is the base in this new picture over here?
4.
4. And the height is what?
112.
1 over 12, yeah. So the height's going to be 1 over 12 for all the parts. The base is 4 because it's 7 minus 3. You subtract the numbers, 7 minus 3, so you get 4. 4, and then 4 times 1 over 12 is 4 over 12. And again, you could leave the answer like that, but because I'm going to ask you to explain the meaning in a second, I'm going to write it as a decimal. It's 33.33%. All right, that's part B. Questions on part B? Okay, let's do part C. Probability we get a number between 8 and 10. Again, we got a random variable, got a bag of numbers. We're going to draw one number out of the bag, and this is saying if you were to draw one number out of the bag, what's the probability you get a number between 8 and 10? Again, we'll draw a picture first. But I'm drawing a picture of a uniform distribution from 3 to 15. And the height of it is 1 over 12. So I start with this picture for every part. Now let's go look at the question. Probably get a number between 8 and 10. So I have to locate the number 8. It's somewhere between 3 and 15. Doesn't matter exactly where, but put a tick mark somewhere, label it 8, and go up to the curve. Then the number 10 is also somewhere between, well, it's between 8 and 15, so somewhere there. Put a tick mark, go up to the curve. And we're going to shade an area, again, below the curve, above the x-axis, and between those two lines. This area over here. This area is the probability that I'm looking for in part C. Now, this is also a rectangle, so the answer to this is going to be base times height, but base times height in this picture now. What's the base in this picture? Someone tell me the base.
2.
2. Yeah, it's 10 minus 8. You subtract the numbers, 2. The height is what?
1 over 12.
1 over 12 again. So the answer is 2 over 12. And again, you could leave it like that unless I ask you to explain the meaning. If I don't ask you on the quiz to explain the meaning, you just leave it like that. Or if I do ask you to explain the meaning, then you want to change it to a decimal. I'm sorry, change it to a percent. As a percent, this is 16.67%. Questions on that one? Okay, sounds good. Let's go to the next one. Probably x is between 10 and 22. Again, we've got a bag of numbers. I'm going to draw one number What's the probability the number I get is between 10 and 22? That's what's being asked of you here. Again, I'm going to draw a picture of a uniform distribution from 3 to 15 with height 1 over 12. All right, now let's locate these numbers. Okay, first number is 10. So 10 is between 3 and 15 somewhere. Let's say it's like there. Put the number 10 there, go up to the curve. The other number is 22. 22 is past 15. So, you know, it's like over here somewhere. It's beyond the curve. So that means 22 has no chance of happening. You have no chance of drawing the number 22. 22 is not even in the bag, okay? And actually, every number past 15 up to all the way up to 22, all these numbers have no chance of coming out of the bag. So what you have to do in that situation is you have to rewrite the problem. So let's go ahead and rewrite it. It's going to be probability. So the probability of getting a number out of the bag between 10 and 22 is the same as the probability of getting a number out of the bag between what and what?
10 and 15.
10 and 15.
10 and 15. So you rewrite it like that. You throw out this part because it has no chance of happening. Okay, and now that you've rewritten that, now the numbers are 10 and 15. And see, that's why it's very important. If you just subtract the numbers to get the base, you might do 22 minus 10 and say the base is 12, but it's not. You have to rewrite the problem first so you know what the correct numbers are to use. You have to use 10 and 15. And then to find the base, you subtract those numbers. You can see over here, you subtract those numbers. Anyway, let me shade the area first. Make sure you're shading all these areas. It's a rectangle again. So the area of rectangle is base times height again. What's the base in this problem?
5.
5.
Okay, and then the height?
1 over 12.
1 over 12. And again, you can just leave the answer as 5 over 12. But I'm going to write it as a percent. It's 41.67% if you do that on the calculator. And that's part D. Any questions? All right, sounds good. Let's go to part E. Probability x equals 7. This is a continuous random variable. What's the answer?
0.
0, yeah. And again, you could just leave it as 0. I'm going to write it as a percent because I'm going to explain the meaning in a minute. All right. Any questions on this slide here? All right, sounds good. The next one is going to say, explain the meaning of all these probabilities. Again, I'll explain the meaning of the first one, and then you guys can help me out with the other ones. So the one from part B said probability you get a number between 3 and 7. The answer was 33.33%. What does this mean? Again, the way I want you to explain it is, if you draw a number out of the bag that has this probability distribution, meaning uniform from 3 to 15. You don't have to write uniform from 3 to 15. Just to save us on words, for all these problems, I'm having you say it the same way. If you draw a number out of the bag that has this probability distribution, the one that's in this question, many times, then you'll get a number between 3 and 7 about 33.33% of the time. Let me write that down. If you draw a number out of the bag, out of a bag that has this probability distribution many times. Make sure you put many times, because anytime you're explaining a probability, you got to say many times. Okay, so if you do whatever we're doing, drawing a number out of a bag many times, this will happen. Okay, so you'll get a number between 3 and 7. About, again, about is another important one. Don't forget that one. about whatever the probability is percent of the time, about 33.33% of the time. Okay, so I'm just going to write that one out for you. Then the other ones are basically similar. Once again, I'll wait a few seconds in case anyone is copying it, and then I'll have you guys help me with the other ones. So just a few seconds here. While I'm waiting, if anyone has any questions. Anyone have any questions? Okay, so let me just wait maybe 10 more seconds. All right. So now we'll go and look at the other ones, and I want you guys to help me explain the meaning. And again, you're going to say it very similar. You're going to basically say the same thing. You're going to change this part to whatever the event is, and you change this to whatever the probability is in the question that we look at. All right, so let's go to this one. Someone explain the meaning of that 16.67% probability.
If you draw a number out of a bag that has this probability distribution many times, you'll get a number between 8 and 10 about 16.67% of the time.
Right. Yeah, just like that. Cool. All right, let's go to the next one. So this one now, someone else try to explain the meaning. And when you explain the meaning, use the numbers that were in the original question for this one. All right, someone explain it.
If one were to pick a number from a bag with this probability distribution, they would draw a number between, many times, they would draw a number between 10 and 22 about 41.67% of the time.
Exactly. I'm glad you caught yourself on the many times. All right, perfect. All right, and I'll go ahead and explain this one. Again, what you would say here is if you draw a number out of the bag that has this probability distribution many times, you'll get the number 7 about 0% of the time. Okay, we're almost done with example 2. I have one last little thing to say, but any questions so far? Okay, so last thing I want to say for this problem, in the last problem, I didn't ask you check the requirements for a probability distribution. So we did it at the end. This time we did it at the beginning, but now I didn't ask you another question. What are the possible values of X? So if I ask you that, so what's the answer to that? What are all possible values of X? Which, before you answer, I'm basically asking, what are all the different numbers in the bag? All right, someone tell me the answer. What are all possible values of X in this problem?
Any number between 3 and 15?
Yes, but write decimal, okay?
Okay,
So
decimals.
are all
Decimal.
decimals between 3 and 15?
And we can say real numbers too, right? Like on a
You
quiz
can
test.
say real numbers too, yes, yeah.
Cool.
But the thing is, if you say any number, it's not like you're wrong, you're right. But if I say, tell me all the numbers between 3 and 6, some people will say 3, 4, 5, 6. I'm like, well, okay, those aren't all the numbers between 3 and 6. So I want to make sure we're thinking the same thing. But if you write decimal, I know you're thinking the same thing. You know what I mean? So that's all. So just when you say between, are you talking about just the whole numbers between? No, we're talking about every decimal you can think of. So decimal just makes it more clear. All right, so one more time. For the answer to what are all possible values of X, in this problem, it's all decimals between 3 and 15. Whatever the interval is, that's basically what it is. It's all the numbers between there and there, but it's every number imaginable, any decimal or any real number between 3 and 15. Okay, we're done with example 2. Questions on example 2. Okay, so we did 2 examples. Again, when I say random variable, you think of bag of numbers. If we're talking about a continuous random variable, then we're going to have these curves. So the example 1, I gave you the curve, and a lot of stuff was labeled for you and asked you to find all these things. In example 2, I said uniform distribution, so you need to know that the curve is a horizontal line. And then once you know that, and you know the area of a rectangle is base times height, then you can answer all these questions. Now we're going to go to, from these two simple problems, let's say, to the most important one at a period, which is called normal distributions. There's a lot of different ones, but this is another curve now, okay? And it's the most important one in this entire class. And we're going to do the same kind of things, you know. I'm going to ask you things like, what are all possible values of x? And find some probabilities, which means you're going to find some areas. Normal distributions. Okay. A lot of times I ask students, do you know what a normal distribution is? They'll say no, and then I'll say, do you know what a bell curve is? And then they'll say yes. That's basically what a normal distribution is. It's a bell curve. Normal distributions, the graph, okay, if this is the number line, the x-axis, and then the graph looks like this. All normal distributions look like this. Okay? And again, we want to be like, okay, from here to here, let's find the probability. So we got to find this kind of area, that kind of thing. So we're going to be working on these now, normal distributions. What do we need to know about normal distributions? First of all, there's lots of different ones. Actually, let me just click through this first. All right. So the random variable x has a normal distribution if its density curve is the function. Okay, I'm going to give you a formula. So you know how, like, when you've graphed something like y equal x squared or f of x equals x squared, and we know that, like, that's a parabola, looks something like this. Okay, so it's one a lot of people know. Every curve has a formula like that. Okay, so normal distribution has a formula as well. And here's the formula. So normal distributions have this formula for the thing you're going to graph. It's 1 over sigma squared to 2 pi e to the negative x minus mu squared over 2 sigma squared. You look at that, you go, what the heck? And if that's what you're thinking, my answer is don't worry about it. You don't need to know the formula. I'm just letting you know it has a formula. But more important for us is that the graph looks like this. Every normal distribution looks like this. This is the curve. And then this is the x-axis on the bottom, okay, the number line on the bottom. But the curve is just that part there. Now, I see students draw this curve really, I was trying to make up a word there.
Creatively.
Huh?
Creatively.
Sure, okay. But I've seen some weird stuff. So draw it right, okay? Like, for example, I've seen a student draw like this. I don't know what's going on there, okay? When you draw a normal distribution, this is what you do. You draw some kind of hill here, some kind of bump. But then you start bending the other way and get closer and closer to the x-axis, but you never touch it. And the graph goes to the right forever. You don't have to put this arrow, but I'll just put it once. The graph goes to the right forever. And on the other side, same thing. At some point, you got to bend the other way and get closer and closer to the x-axis without touching it, and it goes to the left forever. So the graph goes to the left and right forever. It never touches the x-axis, but it gets closer the further you go to the right, the further you go to the left. So if I ask you, remember, this curve is supposed to be describing some bag of numbers. So if I say we have a bag of numbers and it has a normal distribution, and I say, what are all possible values of x? I'm saying, what are all the numbers in the bag? Which numbers are in the bag? Someone tell me.
All of them? All real numbers?
All real numbers, yeah, or all decimals. If I ever ask you, what are all possible values of x, and it's a normal distribution, it's going to be all decimals or all real numbers. Again, the way you imagine is you imagine this curve, imagine the entire curve just falls down to the x-axis, and what will happen, which part of the x-axis will have a curve on it, the entire x-axis will be covered. So all decimals would be the answer. You can write all decimals, you can write all real numbers. It should say that over here. Oh, okay, sorry, we'll get to that in a minute. Okay, so possible values are all real numbers. Okay, another thing is there's many different normal distributions. So I can't just give you a problem and I say, here's a normal distribution, find some probabilities. You can't, because you need to know which normal distribution am I talking about. In order to specify which normal distribution we're talking about, you got to tell me two things first. You got to tell me the mean or the expected value and the standard deviation. So in problems, I'll say like, okay, you have a normal distribution, the mean is 10, standard deviation is 2, now go find some things. So I have to give you the mean, which is over here, and I have to give you the standard deviation, and then you know which normal distribution you're talking about. The mean is where the peak is. If you go to the top of the peak down to the number line here, that number there is the mean. So, you know, if the mean is like 10, then like your normal distribution would be like over here. If the mean is like 30, then your normal distribution will be more over here. So different numbers for the mean could move the normal distribution left and right. So a really big mean, it's really far to the right where the bump is. If it's really small, it's like, you know, far to the left kind of thing. that's the first thing. The mean is where the peak is. It's the number on the x-axis where the peak is. Okay, that's the first thing. And then once you tell me where that is, let's say you say the mean is 10. Okay, so I know it's like the first one. Then the standard deviation tells me, what does standard deviation tell you in general? It tells you how spread out things are, right? That's what standard deviations do, measure how spread out numbers are. For a normal distribution, it kind of tells me how wide the peak is. So the bigger standard deviation, the wider it is, the smaller the standard deviation, the narrower it is. So for example, if I said the standard deviation is 2, then it might be like a really narrow peak like this. And so that might be for standard deviation 2. If I said standard deviation is 10, then it might be a fatter, a wider kind of peak like that. Okay, so that's why you got to know them both. So you got to know the mean and standard deviation so you know which one we're working with. Now to be a little bit more clear about it, let me just go over it again. So again, there's many normal distributions. In order for you to tell me which one it is, you got to tell me the mean and standard deviation. The mean, if you draw a dotted line from the peak down to the x-axis on the bottom, that number is the mean. And the standard deviation, to be technically correct, here's the deal. Where's the standard deviation in the picture? The standard deviation is half the width of the peak if you measure from the inflection point. Now you're like, what the heck is he talking about? Okay, I'm going to take you to calculus real quick. In Calc 1, we talk about graphing curves, and I tell them every curve is made up of happy faces and sad faces. Like if you look at this curve, look at this portion here, it looks like a sad face. Okay, if you look at just this portion here, it looks like half of a happy face. I mean, the rest of it would be, like that. Okay, and here, same thing. This part looks like part of a happy face. The rest of it would be like that. So this curve is made up of happy faces and sad faces. If you look at this curve, it's like happy for a while, and then all of a sudden it bends the other way, and now it's sad for a while, and then it bends the other way, and now it's happy again. The point on the curve where the mood changes, where it changes from happy to sad, there's a point like maybe like here, where you see it's happy afterwards, but it's sad before. There's another point like here, where again, it's sad on this side and happy on this side. Those are called inflection points. So this graph actually has 2 of them, but if you just look at the one over here on this side, again, where it changes from sad to happy afterwards, if you go from that inflection point and you go to the left to the peak, that distance is sigma. So sigma is like half the width of the peak if you measure it from this inflection point. Okay, you don't need to know that. You might need to know that for online homework. Okay, so just so you know. All right, let's click through the rest of this. What does it say here? So the expected value is mu. That's like the average of all the numbers in the bag. That's where the peak is. Okay, if you go from the peak down to the x-axis, that's mu. The standard deviation is sigma. It's half the width of the peak if you measure it from the inflection point. The possible values of x are all real numbers. We already said that, all decimals. Okay, and again, let me remind you that there's many different normal distributions. So if we're doing a problem involving a normal distribution, I got to tell you what the mean and standard deviation are before we can do the problem. Okay. All right, we'll do problems in a minute. Let's go to the next thing. So now there's one normal distribution that's very important. That one is called the standard normal distribution. So there's many normal distributions. One of them is called the standard one, the standard normal distribution. Okay, and what is the standard normal distribution? It's going to look, most of the stuff from the last slide is going to be the same, but here's what you need to remember. Please remember it. It's going to be like 3 points on the quiz next time if you remember it. Standard normal distribution is the normal distribution where the mean is 0 and the standard deviation is 1. So you're going to memorize that. If it says standard normal distribution, actually, let me back up. If I say normal distribution, I have to tell you the mean and standard deviation. I have to tell you both of those. But if I use the word standard, then I'm not going to tell you what the mean and standard deviation are, because you need to know that there's 0 and 1. Mean is 0, standard deviation is 1. And so what that means is, okay, so standard normal distribution is the normal distribution where the mean is 0, standard deviation is 1. The formula for it is this. All I did was I took the formula from the last slide, and everywhere it said mu, I put 0. Everywhere it said sigma, I put 1. And it's simplified to this. Again, you don't need to know it, but it's there in case you're interested. That's the formula for the curve. If you graph the curve, it looks like this. What's the difference? The mean is where you go, if you go from the peak down to the x-axis, that's the mean, but now I put a 0 because the mean is 0. And if you go from the inflection point and measure half the width of the peak, that's sigma, but now sigma's 1. So I just change it to 0 and 1 over there. Okay. And not much else to tell you. One last thing to tell you. If it's standard normal distribution, we're not going to use the letter x. Normally, for a random variable, we use the letter x. But for standard normal distribution, we're going to be using the letter z. That's reserved. Anytime you see the letter z, you're like, oh, he's talking about standard normal distribution for this one. All right, let me click through the rest of this. So the expected value is 0. The mean is 0. Standard deviation is 1. The possible values are still all real numbers. That's the way it is for every normal distribution, including the standard normal distribution. And for the standard normal distribution, we are going to use the letter z instead of the letter x. Okay, so this is the most important probability distribution. And what's our job now? Now what we have to do is we have to learn how to find areas under these things. How do you find probabilities or areas under these things? So that's the next thing we're going to do. We are going to do that next class. So we are done for today.